Okay, guys, so chapter 5 is a continuation of some physical concepts that we need to understand before we go into the study of stars, galaxies, and the universe as a whole. We need to understand how light interacts with matter, how do we measure light, and how do we represent, what do we use to represent light in or theoretically. All right. So for this, we need to bring on a few concepts from physics, a few from chemistry, but at the end of the day, we will be studying the interactions of light and matter, the composition of light, what is light, and we are going to be doing again the phases of matter, and towards the end, how this relates to the study of objects in the night sky. For example, we've been talking about stars and planets. We know what's the difference between both of those. But when we look at, for example, stars or galaxies, so let me show you a few pictures we have here in the observatory. Right? So when you see, for example, this picture here from NGC 470, there, the spiral there, and NGC 474, and then you see other objects here with different colors. By the way, those are spherical galaxies there. And then on the background, you can have other galaxies and other, maybe in some cases, the smaller objects are stars, okay? You see different colors. For example, look at this, this Tarantula Nebula, which is a supernova remnant. You see the different colors surrounding it, and then here on the center, where most of the radiation is coming from. And then you have another nebula here, like the Orion Nebula, and you see the characteristic colors, and then you see other objects. These are the stars, actually, bluish stars. But then here at the bottom, you have like a reddish star. So why do they have different colors? Well, we see light, but how do we measure that light? How do we measure the intensity? That's one of the objectives of this, one of the goals of this chapter. But to understand that, we need to know what light is. Okay, so first of all, let me show you the following picture. So what you're seeing there is the characteristic spectrum of the sun. So when you look at the sun, it seems yellow because we are seeing the sun, or part of the light of the sun, being absorbed by atoms in the atmosphere. And we also see the refraction and dispersion of light. However, if we are outside of the atmosphere, we will see the light of the sun being white, which is a combination of all the colors. It's the rainbow colors, right? As you see there, from red to blue, well, purple, but what you see there is from red to blue. And the major characteristic is that there are gaps. So what are those gaps? At the beginning, we're talking about when we started investigating this a few, maybe 100 years, almost a century ago, we were not quite sure what were those gaps. I'm talking about the black lines in here. Later on, when we studied other objects in the sky, we realized that different stars will have gaps in different places. We also studied the spectra of the light reflected from planets and moons like Titan, Ganymede, Mars, Enceladus, a moon of Saturn, Europa. So we see that they have gaps as well. The spectrum doesn't look like this, by the way, right? If there were no gaps, this would be a nice continuum spectrum, like the rainbow that you can see when there's rain during a sunny day. So these gaps, we now know, are due to the atmosphere or the atoms surrounding the per se atmosphere of different stars. We know that the outer layer of the sun has three different layers, and we want to study the photosphere, the chromosphere, right? And the corona, but there are atoms absorbing the light being radiated by the sun due to, the light being produced by nuclear fusion in the core. And those lines are due to different elements. What you're seeing there right now are fingerprints of those elements on the outer part of the sun. Normally hydrogen, a little bit of helium, but there can be other elements also being produced. So we can study that using emission and absorption lines. Okay, so how do we experience light? By, for example, feeling or looking at the sun. How does the light interact with matter? By looking at other objects. Objects reflect light. So normally you will see that colors are basically emissions of wavelengths. So why do we call it wavelength? But that's something that we are also going to introduce today. So the warmth of the sunlight is telling you that light is a form of energy. That's correct. And we measure that energy in watts, which is 1 joule per second. Joule, as you remember, is the unit of energy, and second is unit of time. So energy divided by time is power, which is watts. The other way we call it in astronomy or in astrophysics is luminosity. The power radiated by a star is also called the luminosity of the star. Now, you probably have seen this before in a physics lab. When you have a white light going through a slit, it's one slit, and then you put a prism, you will see light being refracted. So basically, what you guys have is you have there an spectrometer. An spectrometer is a device that we use in astronomy to break light into its components. Okay? Now, as I said, white light is made up of all the colors of the rainbow. What you're seeing right now in there is the continuous spectrum. That's a spectra that you will expect from the sun. And a spectrometer normally looks like this. This is a spectrometer that we use normally for high school and college. And the way this works is you will look at any source of light from this eyepiece, and then you will see here lines depending on the type of object, right? If you're looking at an incandescent light bulb, you should see it should be continuum. But I'm going to show you later what type of objects will emanate those lines that you see there in the continuous spectrum of the sun, this one here, right? As you can see here, this is continuous without gaps. There's nothing in between the light source and, the light, what you're seeing here, except the prism. But the prism is just there to break up the light. So we have emission lines, absorption lines, but we also have transmission. Transparent objects, they just transmit light. Opaque objects, they block light. Now, when we talk about light, I don't want to go ahead too much, but what we are seeing right now in terms of the visible part of the spectrum, that is just a very narrow part of the spectrum. If you think about it, right, we have radio wave, microwave, infrared waves. Infrared is what you are using a lot nowadays when you go to the gym or when you go to college or when you go to certain places where they take your temperature. That they use an infrared thermometer. Microwave is what you use for cooking. And radio waves is what you use when you are listening to the radio in the car, right? So we have already a glimpse of other emissions, right? Now, reflection, we are going to study this more in the next chapter. Just remember that a perfect reflection is what you're seeing here. So light can be reflected in a mirror, smooth and plain. And you have here the angles to be equal to each other. That's called regular reflection. Okay, and that normally happens in a plane mirror. Okay, we take advantage of that, for example, in a projection booth, and when you have a movie theater, right? When you're looking at that, you can see how light is being reflected towards you, right? You also experience it when you're looking at the rear side mirror, right? The mirror that you have inside the car and outside the car, right? One is to look at objects that are on the left-hand side or the right-hand side of your car. So they use the idea of reflection, right? Of course, we are going to learn later that there are different types of mirrors, not just plain mirrors. So the interaction, that's one example of the interaction of light with matter, right? Reflection. Refraction is another one, but the way, for example, the sun or a lamp are emitting light and how it's being reflected towards you, your eye, and how you're actually looking at it. Now, the idea of scattering is also a very important concept of how light interacts with matter. For example, a typical question is why the sky is blue? And the incorrect answer that you will always hear from people, even from people that have done some sort of science in high school, is because the water of the ocean is being reflected on the sky, right? Which is incorrect. The reason why light is blue is because, as we know, and this is a good representation, the light of the sun, which is white, is being refracted and dispersed, scattered in the upper atmosphere. And what happens is that some of the atoms are absorbing the spectra of light, the spectrum of that visible light. And they are scattering mostly the blue part of the spectrum, which is why you see that. That's called the Rayleigh scattering, by the way. So the sky is blue because of that. Now, during sunset, the position of the sun changes, right? Because now is on the horizon. So light is going to travel a little bit more or a major distance than when it's on the top. Also, the scattered blue light is already being scattered during the day, and the leftovers are the orange red part of the spectrum. So that's why sunset is orange reddish. It's around 6 p.m., 5 p.m., and 6, 7 p.m. during summer. Okay. We also notice polarization during sunset, by the way. All right, which is due to the position of the sun. So why is an object red? Why is a rose red? Because the rose absorbs? No. Because the rose transmits? No. The rose emits? No. The rose reflects red light. Okay, so the rose reflects red light, so it's basically that part of the spectrum is being reflected by the rose. When we look at the spectrum of planets, for example, when we investigate exoplanets, when NASA is looking at exoplanets that are thousands of light years or hundreds of thousands of light years away from us, what we obtain, besides a picture of the planet, is we know the composition of the planet and the composition of the atmosphere. How do we know that? With certain precision, because we can study the spectrum reflected by the planet, and we know what elements are in the atmosphere of that planet. That's how we know. We can also do that with a neighboring star. Okay? So light is a form of energy. Light comes in many colors. If they are combined, we get the white light. And we have scattering, reflection, and we have the lines of emission, absorption of the spectrum. All right? So that's the introduction of what light is. But what is light? Well, let me show you on the whiteboard what light is. So if you guys are ever interested in physics, once you do electricity and magnetism, and you combine both, they will show you the following picture. So in 3D, so this is the X, Y, and the Z axis. What they show you is that electricity and magnetism were combined by James Maxwell at the end of the 19th century. Yeah. And he realized that light is a wave that has a component of electric field, but also has a component perpendicular to this of magnetic field. With the same period, but with a different wavelength. Sorry, with the same period, same wavelength, with a different amplitude. So we label this B for magnetic field. Yeah, we don't label it M because M is used for other things like mass. So B is magnetic field and E will be the electric field, right? What we know is that they are perpendicular to each other and the propagation is alongside the x-axis. If E vibrates on the y-axis and B vibrates on the z-axis, the direction of propagation is perpendicular to both, which is the x direction. And E and B are perpendicular to each other. This is an electromagnetic wave. This is light. The light that I'm using right now here, or that you're using in your house or in the office, that is this. Of course, we don't see this, right? Because what's the speed of this light? Is the speed of light, which we label it as C. Okay, so that is the speed of light. And we know the speed of light already, 300,000 kilometers per second. So that's extremely fast. But that's how this is propagating. All right. So a few characteristics. Look, this is a 3D representation. Okay. The parameters for a wave are the speed, the wavelength, lambda. We use Greek symbols for that. And frequency. So visible light, any component can be characterized by this. What we know is that blue has a higher frequency and a lower wavelength. Red has a lower frequency and a higher wavelength. It goes from 400 to 700 nanometers. What's a nanometer? A nanometer, which we label it like this. You're seeing that, right? Yeah. A nanometer is 10 to the negative 9 meters, extremely short. Okay. Moreover, the visible spectrum is the narrowest part of the spectrum of light. Because as I said, light comes in different flavors. You have radio, microwave, infrared, visible, and then we have, well, right, we're gonna go there in a second. Now, how can we do this a bit, how can we draw this a bit more easily? Well, you can always project this to the plane. So in the slides, they also show you this. They will show you in the X, you can just put here like that. You can just put this as X and this as time, and you will have like that. Or you can leave this as X and Y, just to keep it more simple. This is the amplitude of the wave. We don't really care much about it. In physics we do, but for now, we care more about the period and the frequency. Let me show you why in a second. The wavelength is the distance between two peaks. And the period is how long it takes for one wavelength to travel. So this is traveling at speed of light, right? We know from physics, and you know from the previous chapter, distance over time is speed. So this is the distance, and this distance is traveling one period. So period is labeled as this, which is the inverse of frequency. So we say that distance over time period is equal to c. And that's the first mathematical relationship for electromagnetic waves. We will get that if we define 1 over period as frequency, which is the number of cycles per second, you will get lambda times frequency equals to the speed of light. This is important. Because now you can see that when one goes up, the other one will go down. Because the speed of light is always constant, right, in the universe. There you are. So that's the equation that you also have in the slides. And this is a representation of an electromagnetic wave. Okay. Now, of course, we're dealing with very big or very small numbers, depending on what you are doing there, and depending on what part of the spectrum we are looking at. Okay, so that's the next part. Are there any questions about this?
Yeah, Professor, I have a question.
Yeah.
Yeah, so can you go over, like, how did you get 1 over t equals frequency? From
That is a definition.
Oh, okay.
That's a definition, because period is, for example, the period of a satellite, the period of the Earth around the sun is 365 days. But if you want to measure how many times it can do it per second, you will do the inverse of that. Day, because that will be in days.
Okay.
Right? So that's just a definition. Okay. All right. Okay. So we know light is a wave. We know that from the 17th century, actually, they realized. It was the first realization about light. Who has heard about Young's double slit experiment? Okay. Let me ask you something. If you have two slits, let's stop this. If I give you two slits, okay, and you pass light through them, and there is the wall over there, how many slits do you see in the wall? On the wall. So this is light. This is my source of light. And the slits are not that separated. Right like that. See like that, right there. What will I see here? How many slits will I see? So classically, people thought that they would see two slits. So light is going through two slits. What they realized, what they saw, what Young saw was several slits with different intensities. The biggest one was in the center. How is that possible? Because light behaves as a wave. Okay, let me give you the same experiment with water. If you have two slits and I give you water like this, going through the slits, water will be going in different directions, right? Because water, the water waves are interfering with each other as they go through the slits. They realize that light has also a waterish behavior. It has a wave behavior. It's what you see when you throw a rock on a pond. You see these wavefronts? That's what happens with light as well. So light is a wave and carries energy with it. That's why you see and you feel the energy and you see light. However, later on we realize, thanks to Albert Einstein, that light is also made of very small bundles of light that we call photons. So light is also made of a stream of particles called photons. So we realize that light has a dual behavior as a wave, as a particle. Now, depending on the experiment, light behaves accordingly to the experiment. For example, if light is going through slits, we see the wave behavior of light. If light is being radiated towards a piece of metal, light has a particle behavior because there is a momentum. Photons, as they collide with the metal, are removing electrons. The only way they can happen if there is an interaction between the photons and the electrons, a conservation of energy and momentum. Okay, so look at the representation of wave in there, wavelength and frequency, and there is the relationship I gave you. Okay. By the way, guys, for mechanical waves, the waves that you can produce at home or when you are, again, you probably have done this if you exercise in the gym, you see that when you produce waves, right? That wave, that speed is also wavelength and frequency. Okay. And there you are. So those electrons that you are seeing there are the ones moving as light passes by. And why is that? Because as I said, light is made of an electric field and a magnetic field. So the electric field and the magnetic field, they can carry on and push electrons because they produce a force on the electrons. Okay, so that's how light interacts with charged particles. That's how the light of the sun interacts with the atoms in the atmosphere because of the electric and magnetic field. Okay. So look at the way we measure wavelengths and look at the units, right? So we have a wavelength of 1 centimeter, of 0.1, of 0.5, and 0.25. So the shorter the wavelength, the larger the frequency. And look at this, gigahertz. I mean, if you guys like computers, if you guys deal with computers every day, you should know what's a gigahertz. Gigahertz is a unit that we use to measure the, I don't want to say speed, but the efficiency of a microprocessor. When you guys buy a computer, or if you're going to build one, right? Don't just look at the Core i7, AMD, Core i5, or whatever. You have to look at that particular value, at the frequency of that microprocessor, because it's telling you, that is actually telling you the performance of the computer. Besides the memory. Okay, so normally microchips come nowadays almost at 4 gigahertz, I want to believe. I don't remember, but they have the turbo option as well. But the higher the value, the more expensive the computer is. Okay, so that gigahertz is 10 to the 12 hertz. And hertz is the unit of frequency. Instead of calling 1/2, we say hertz, in name of another scientist that investigated all that. The thing about electromagnetic radiation, it was investigated not just by Maxwell, but we have Tesla, Hertz, we have Newton as well, we have also Einstein, right? But mainly, we mainly remember James Maxwell because he's the one who unified electricity and magnetism. Okay. Now, particles of light is a photon, and we can measure the energy of the photon. So here we have another equation. All right. So we have that equation. Let me show you how do we measure the energy of light. Well, a stream of light can have billions, trillions, quadrillions, quintillions of photons, more than that, right? And large amount of photons. The energy of a photon is given by a constant value h times the frequency of light. Or, as we did before, right? C over lambda is frequency, so H, C over lambda. Now, what's H? Well, you probably have heard about this name. H is the Planck constant. It's another scientist from the golden era of physics, the beginning of last century. Planck constant, which is measured to be 6.626 times 10 to the negative 34 joules second. Okay, so that is, so it looks very small, but remember, we have a very large amount of photons. So when you multiply by the frequency, which can be in gigahertz, 10 to the 12, it makes it less, it makes it greater. And then if you multiply by the number of photons, you get an enormous amount of energy. All right? See, right? Joules per second, because the unit of frequency is 1 over seconds, or hertz. So that's how you get joules in here. So that's another important equation, okay? Now, let me do a couple of, because I know that you might need to remember some of this. So let's see how we can use this with real numbers. First of all, let's do the speed of light and the wavelength, all right? So let's use 5 centimeters. So let's say they give you lambda equals to 5 centimeters, and they want you to compute the frequency. If that's the case, what you will do is you will say, okay, well, I know C equals to lambda times frequency. And what's C? C is 3 times 10 to the 8, because I'm writing in meters per second. I know lambda, but I don't write 5. 1 meter is 100 centimeters. So we divide 5 by 100, or we use powers of 10. 5 times 10 to the negative 2, that's in meters, times the frequency. Okay, so 3 divided by 5 here. And let's see, 10 to the 8 is divided by 10 to the negative 2. When you have this type of divisions, the same base with different exponents, in a division you subtract the exponent. So 8 minus 2 is 10 to the 10. And 3 over 5 is 0.6. So this is around 0.6 times 10 to the 10 hertz. But we normally don't leave it like that. What we do is we move the 0, 1. If I do that, I move the 0 here. I take 1 0 from here and I put it there. So I multiply by 10 and I divide by 10. Or I subtract the exponent by 1. I get 9. So this will be 6 times 10 to the 9 hertz. All right. How many of you have questions about this math? What I'm using right now is just law of exponents for this division, and you can always use a calculator for 3 over 5.6. Okay, you see how important is powers of 10. So even though you probably want to have just one question, maybe 2 in an exam, it's always important that you use powers of 10. Even for the previous chapter, because masses are, for example, the mass of the Earth is 6 times 10 to a 5.997 times 10 to a 24 kilograms. So in astronomy, we use very large numbers and sometimes very small numbers. So we have to use scientific notation. Now, let's see if I want to use this frequency to find the energy of this wavelength, of this light. So I already found the frequency, 6 times 10 to the 9. Now let's use the Planck equation. So the energy is H times frequency. What's H? 6.626 times 10 to the negative 34 times this was 6 times 10 to the 9. Okay, now we're doing multiplication. 10 to the negative 34 times 10 to the 9, you add the exponents in this case. But negative 34 plus 9 is negative 23. And 6.626 times 6, well, in that case, you have to use a calculator, right? So I get almost 40. So 40 times 10 to the negative 23, what? Joules. Now, do I leave it like that? No, because you see 40, so I can put 4 times 10 to the, this 0 goes here, so negative 23 times 10, negative 22 joules. Okay, so that's how we use these equations. All right. Any questions? I mean, these are the only two. There's one more that we're gonna do towards the end, but we're gonna use it in the lab as well. Okay, but this one is just for reference, so you know that's the Planck equation, and the previous one was the equation for the speed of the wave. So there they are. Here it is, guys. All right. Planck constant, the speed of light, frequency, and what the labels are for each of those. Okay. Yes, there will be 1 or 2 exercises of this. Maybe not in the assignment, but in the web project. Okay. Okay, we talk about that. There it is. This is a very important slide for exam or for a quiz or for like any sort of reference. You need to know this because this is showing you the full spectrum or the full electromagnetic spectrum. As I said at the beginning, the visible part of the spectrum is very narrow. It's only that. And as you can see, we have a whole bunch of radiation that we cannot observe here on Earth because the atmosphere of the Earth is protected, or in other words, is opaque to that other radiation. What is that? Infrared for its majority, microwave, ultraviolet, most of it, part of it can actually be observed, but only by certain animals. X-rays and gamma rays. So, well, radio waves only part of it is actually transparent. The atmosphere is blocking part of the radio waves. Some of them actually, they can make it through, and that's how we use radio waves as well here on Earth. But the main idea is that you see how gamma rays are, or they have a very short wavelength. And you probably have heard about X-rays and how they were discovered and how they can be used in medicine. So they are highly energetic and very dangerous, right? How many of you remember? Okay, here is where I'm gonna evaluate you guys. Where have you heard gamma rays before? And you have heard it this semester?
The Death Star video?
Exactly. Good. You heard that in the Death Star video, gamma ray bursts. When a supernova explodes, when a star goes under a supernova, those jets, right, they can emit these gamma ray bursts. And if they are aligned, not necessarily at a close distance to the Earth, they can actually vaporize the atmosphere and produce a massive extinction event, as we believe happened a few hundred million years ago. That's another topic. So gamma rays and X-rays, we cannot really investigate them from the Earth. If we want to observe a black hole, we need to have a telescope, for example, like the one in, I forgot the name, the one that discovers Cygnus X. All right, the Chandra telescope, there you are. That telescope is located in the upper atmosphere, is orbiting the Earth, because X-rays cannot be measured from the ground. Okay, what we can measure from the ground are visible, but a black hole doesn't emit light. We can actually investigate a little bit of microwaves and radio waves. And I know that very well because that's what I use to investigate Sagittarius A star. We use radio waves. And we were able to determine part of the what we call the variability as matter is being accreting towards the disk of the black hole, towards the singularity, to the event horizon, sorry. So visible light is everything that you observe right now, but there is a whole bunch of the spectrum that we cannot observe, and we have special tools for that. Now, look at the sizes of their wavelengths. So a radio wave is very large, but very low energetic, right? Look, how do we know it's very low energetic? Because it has a low frequency. And what do we know from here? The lower the frequency, the lower the energy. There you are, that's why. You know what? Everything that you observe in the universe is either between the radio and the gamma rays. But that represents approximately 4% of the universe. When we do cosmology, at the very end, we will learn that 96% of the universe is totally obscure for us in terms of dark matter and dark energy. All this is also called baryonic matter. Okay. All right. Any questions about this? Do you understand why we use a wave? Yeah, right, because it's a wave. It's all a wave, and they all move at the speed of light, by the way. The speed of light is always constant. The only thing that changes is the wavelength and also the frequency by this equation here. Okay, answer this question. The higher the photon energy, A, B, or C?
B.
B.
Yes. Shorter the wavelength. So now you know what light is. Now you know how we can represent it, how we can illustrate it, sorry. You know what photons are? Bundles of light. It's a fundamental particle of quantum of matter, okay? There are 4 fundamental forces of nature. You have learned 2 already, gravity and electromagnetic. The other 2, we're gonna learn it later, but they are the nuclear force, strong and weak. Photon is a fundamental particle for one of the fundamental forces, the electromagnetic force. We cannot see most of the forms of light. Yeah, that's true. We only see this part. So when they tell you that we don't really know much of the universe, that's true though, unfortunately, right? But even though we can only see 4%, we can measure 4% of the universe, we can still have a good idea of how it behaves because we have other forces, gravity, for example. All right, now we're going a little bit into chemistry. What is the structure of matter? Who remembers that from Chemistry 101? What's matter made of? I've been saying that during the whole class.
Helium?
Atoms. Matter made of atoms. And then
That's what I meant.
atoms, what was that? Oh, and then atoms have a nucleus. The nucleus of the atom is made of what? Remember the Thomson Rutherford model, the Bohr model? What did Bohr say in his model? That the nucleus of the atom is made of protons. It's a positive. It's where most of the mass of the atom is stored. It's contained. And you have what orb? Sorry, I'm not going to use that word because it's wrong. What is around the nucleus of the atom? Electrons. All right. So look, guys, what you're seeing right now is the most, not really the most, but it's a better representation of the nucleus of the atom and the atom itself. You probably are used to this. Okay. Well, let me tell you guys that this is totally wrong. This was accepted up until the 1980s, 1990s. However, thanks to Feynman, Schrödinger, thanks to the current developments of quantum physics, now we know that there is not really orbitals. This model is extrapolation of the Bohr model of the atom, which was this here. That was the Bohr model of the atom. Very simple, very nice, very easy to understand. Just one proton, one electron, right? And it resembles the Earth orbiting the sun. There are so many mistakes in there. Again, placing the atom at the nucleus of the proton at the center. That's one mistake. But the major mistake was to believe that the electron had a fixed orbit. That's not correct. Now, it was okay for this very simplistic atom, hydrogen. But when we go to heavier elements, it doesn't work. Now, of course, in some books, they still show you that, but now you're learning that that's incorrect. Now, what's the difference between that and this? That we know that the electrons, right, are in what we call an electron cloud. Who has heard about the Heisenberg probability principle?
Heisenberg.
Certainty
That
principle,
rings
sorry.
a bell.
Huh?
Heisenberg. That rings a bell. Ugh.
That you cannot measure the speed of something at a particular point, something like that. I don't know.
Yes, you cannot measure the speed and position of a given electron with a precision that is like this. So, this is position, inverse proportional to momentum. Why we use momentum? Because momentum has speed in there. Less than or equal to h over 2 pi. So this is the Heisenberg uncertainty principle. I don't need you to memorize this or learn this. The only thing is that if you are measuring the position with a high probability, well, guess what? Your probability to know the speed diminishes, and vice versa. So you know the probability of something popping up here. That's all. So this is the moment where Einstein shied away from quantum mechanics. He said that he couldn't accept a principle based on probability. Right? This is when physics started to be divided into two branches: quantum physics and relativistic physics. Okay, a few properties: atomic number, atomic mass. Atomic number are the number of protons in the nucleus. Atomic mass are number of protons plus number of neutrons. In an element in a periodic table, the number of protons are the same as the number of electrons. unless you have an excess. Like for example, if you have an ionization. Who remembers what's ionization of an atom?
The ionization is what is no wait. They think the polarity like positive, negative. That's polarity. Wait.
Yeah, no, you're right. So what happens when you have an excess of positive charge?
Hmm.
You have a what?
Excess of positive charge. Hmm.
If I write, no carbon. Yeah, if I write carbon plus, what's the meaning of this plus? That means that it has an excess of protons, of 1 proton. Okay, but you can also write carbon, it has an excess of 1 electron. Okay, so unless you have this is the same as number of electrons. Okay, helium, which is the alpha particle, has an atomic mass number of 4, 2 electrons, 2 protons, or 2 protons, 2 neutrons, sorry. Protons and electrons are the same, 2 and 2, but 2 neutrons there, 2 neutrons, 2 protons. Okay. What's an isotope? Who remember what's an isotope of an atom or an element?
Isn't it like one atom is divided into like multiple atoms or something like that?
Sort of, is when you have the same element with different number of neutrons. So then obviously the atomic mass will change. Okay, so carbon 14. Who remembers where we use carbon 14? This isotope is very important for archaeologists and anthropologists.
Radioactive decay?
Radioactive decay, perfect. So these isotopes, they have a radioactive decay, and we use to age, to measure the age of things, right? Is that clear? I mean, that's basically what I want you guys to learn, because that's basically how light is going to interact, by absorbing, by electrons absorbing or emitting photons. Okay, and we're going to learn that in a second. Now, besides this, we're talking about matter now, right? The phases of matter. There's one missing there, right? Plasma. Familiar phases are solid, liquid, and gas. But we also have plasma. Here the ionization, right? When you give so much energy that you start stripping the electrons and you change them into plasma. Now, from lowest to highest, you have melting or fusion, right? So this is the thing. I didn't explain this in chapter 1 and 2. When you guys have solid, liquid, and gas, the main differences are the arrangement and position of particles. Solid has their atoms in fixed positions. Now, they are vibrating, but their vibrations are very hard to be noticed. So we say that they have a fixed volume and a fixed shape. When you start heating them up and you get to a threshold value, you start doing what we call a change of phase. That is a process of melting. You start breaking the chemical bonds in between them. So then the fixed position start becoming more random. They become water. That chemical bond is governed by the potential energy. I did say this in the previous chapter, I think, right? Yeah. So that's the potential energy. That's the intermolecular forces. In chemistry, they normally call them the London and London or the Van der Waals forces. Those are the forces that govern the chemical bonds, ionic and covalent. So then you have the process of evaporation or evaporization is the same. When you are boiling water, for example, those molecules are moving faster The higher the temperature, the faster they move. Because temperature is a measure of the average kinetic energy of particles, okay? Now, you start breaking more and more the bonds, and now they become gas, where they have random motion of molecules. But then you start having dissociation and ionization, and then you start breaking the molecules into atoms, and then you start stripping the electrons from the atoms, and they become plasma. Talking about 5,000, 4,000 kelvins. Is that clear, or you have any question, guys? How many of you have seen this before? Or have heard about this before? Yeah, so that's why we're doing this, because I feel like it's important that you guys know this. This is the very basics of what we're gonna be doing. Now, of course, pressure also plays a very important role. The pressure of the air, of the ocean, humidity. Okay. But now, how is energy stored in atoms? Who has seen this before? Energy levels, excited state, grounded state. So when Bohr came up with this, or this, right? I lost it. What is it? Ah, whatever. He said that the electrons can jump from one level to another. So, I mean, that is not that bad, because that's actually kind of true. You have the Balmer and the Parshen and the bracket lines of emission and absorption. So an electron is normally in the ground state, but it can be excited and it can emit energy or absorb energy. And it can go to different energy levels. The energy levels are given by this picture here. Who can tell me what is this? Here. What am I measuring here? What I'm measuring there is the energy required for the jump. Now you're probably thinking, but what's that EV? EV are electron volts. Is the basically by multiplying the charge of the electron by 1 joule, or by 1 volt, sorry. Okay. Here. You get 1 electron volt, which is 10 to the negative, the charge of the electron is 1.6 times 10 to the negative 19 coulombs volts joules. There it is. Now you know why we use electron volts, because we have very small values of energy. So I don't want to write 3.3 times 10 to a negative 18 or negative 19. So I just write it in electron volts. It's pretty clever, right? This one is not allowed. This transition is allowed. Nothing in between. So that's why they say electrons in atoms are restricted to particular levels and transitions. So why does that matter? Because when a photon, when light is radiating matter and is glowing and reflecting light, the atoms are being excited. Ooh, there it is. And they emit energy governed by this. So you probably don't want to need to know this, but still, the fact that now you know, now you see that there is a reason for that. Don't just believe when they tell you something, right? That's the very basics of science. So there is physics and chemistry. So once you understand the very basics, now we can start understanding why stars radiate and how do they radiate the way they do. Right? So that's that. That's what we learned. The structure of the atom, of matter, and the phases of matter, we review that, and how energy is stored in atoms. All right, guys. Now we're gonna go into kind of joining everything together. Okay. Classically speaking, we measure the power radiated by stars. Perfect. That luminosity, let's remember stellarium. You have different objects, and depending on how far they are, but also depending how big they are, they seem to be more bright. Okay. So the luminosity, which is the power radiated by a star, is given by the solid angle that we are measuring, which is 4 pi. By the size of it, well, this is the area of a sphere, something called the Boltzmann constant, and the surface temperature to the power of 4. That is the classical view, and it still works. When we talk about the power radiated at certain temperature, we can use this equation. However, you have different stars. So when we start using and trying to model the intensity, so when we try to analyze the spectra of just one star, right, across all its wavelengths, not just the surface temperature or not just the one that we are observing, but across all the wavelengths, we try to use the intensity per wavelength. According to this, it should be, you know what? Physicists came up with something called the catastrophe of the ultraviolet catastrophe. Around the ultraviolet wavelength or peak, they realized this when they were using the data points. Something like this happening. Why is it going down? Intensity versus wavelength. Around the ultraviolet here, UV. So this equation doesn't hold in every case, especially if I'm using this type of analysis. Planck came up with a solution. The solution is this. What you're seeing there is the spectra of astrophysical objects across their whole wavelengths. That's the Planck curve, and this actually fits the Planck curve very nicely, which is, by the way, an exponential equation. You can see here, right? Look at this part. This is a classical view. Here is where it starts breaking down. All right. Now, you see these peaks and these lines here and these gaps? So that's when we started to realize that there were some absorption and some emission within the continuum spectrum. So besides knowing how to plot the spectra of these guys, let me show you the experiment that unfortunately we cannot do, all right? But at least you're gonna see it, okay? If you have an incandescent light, or if you use a spectrometer, right, like this towards the sun, you will see a nice rainbow. But then you can use this. So this lamp is a high voltage device, right? What I can put here, I can put a lamp. Hopefully it won't break. Let's put this down there. Can I put this right there? That's okay. So what I'm gonna do here is I'm gonna put a lamp of helium in here. And it goes in here. And I turn it on. And what you see there, if you have one of these, you will see the emission lines of this guy. This is the emission, or this is a lamp of helium. And that spectrometer will allow to break the spectra of helium into its emission lines. We can do that for every other element. This is helium, right? It gets hot really fast because of it's a high voltage. I can also do that for hydrogen, right? So for hydrogen, you saw how that one was a bit reddish, right? So for hydrogen, what we have here is another lamp. Let's put this in here. Let's see what we get. That's your hydrogen lamp. So we can investigate with a spectrometer the emission lines of each element. Why do we do that? Because when we combine the emission lines with a continuum spectrum of the sun or any other star, we can actually start understanding the spectra and how it actually behaves. So there are three types of spectra. There is the continuous, the emission, which is given by what I just showed you, or maybe a cloud of gas, which has several elements, and the absorption. The absorption is probably the main one. You know, this is actually called Kirchhoff rules. Not like the ones from circuits, by the way, but these are Kirchhoff rules or Kirchhoff laws for the study of spectra. Okay. When you look at the sun without anything in between, you will see this. But we know that in between the sun, there are gases. There's an atmosphere. There are elements in that atmosphere. When you combine them, you start seeing this, which is what I showed in the first slide, right? So that explains this and this. These are emission lines. These are absorption lines. Depending on where they are located, we know what element it will be, because we can study the emission lines independently in the lab easily with what I just showed you. And we know at what frequency they occur. By knowing at what frequency / wavelengths they occur, we know what type of elements are. We can identify them. The continuous spectrum can be found from any incandescent bulb. The emission one can be found from any cloud of gas. The thing is that normally they are very cold, molecular clouds, for example, in the universe. So normally there has to be something to trigger them, right? Maybe when they are contracting and fragmenting to start having star formation, okay? And then if you have a star that is passing through a cloud, you have this absorption. And there you are, guys. Right? Everything comes together. Now, we're talking about different elements, hydrogen, helium. Well, now we know, based on what we just did, that matter is made of atoms. Hydrogen has a proton and an electron. Helium has 2 protons, 2 electrons. So when light goes through it, those electrons are being ionized, are excited. That's how energy is being produced, is being emitted. That gives you what? Transition levels. Those transition levels are the ones that you are observing, guys. They are unique for each frequency and wavelength. You see? That's why you have to know this first. And now you can explain the physics behind an emission line. And you can predict at what frequency and wavelength they should happen. Yes, there is an equation for that. 1 over lambda equals to the constant of Rydberg, 1 over n squared minus 1 over n squared. I don't know how many of you have seen that, but there is an equation to know the wavelength for a transition. You don't need to know that, all right? But we have one. Okay, so these are also known as chemical fingerprints, and these are the corresponding wavelengths at which those lines are happening. Those are the transitions from here. If we find a wavelength of a transition from level 5 to level 3, for example, or from level 3 to level 2, we can compute the wavelength and then compare it with the experimental value and see if our prediction aligns with the theory, which actually does. Okay. So because these atoms can absorb photons with the same energies, you have upward transitions, produce patterns of absorption lines, as you see there. Right? If you combine the continuum spectrum, you have this absorption spectrum. Look at the characteristics of helium, what I show you, sodium, and I have neon as well. So you didn't see this when I show you helium, right? You saw a lamp. But to see that, you need a spectrometer, a prism, and it will break into components. So we've done that. Okay. So remember, guys, that molecules have also other additional levels, because remember, molecules also vibrate, as I explained, with a solid, right? They have vibrations, and they also rotate. Okay, so have rotational energy as well. They have some sort of angular momentum. Okay. So if you take that into account, you can have all these energy levels that make up for the spectra of more complicated molecules. And it starts making it more complicated because you have cases where you see something like this. Okay, so you see, depending on where you are looking at, you can have these transitions, these emission and absorption lines happening in different parts of the spectrum, in this case, in the infrared part of the spectrum. Okay, so remember, guys, right? When they ask you about absorption lines, you are looking at here. Oh, sorry, here. All right, and when you're looking at emission lines, like they ask you, I don't know about absorption here. Oh, here, emission lines. So emission lines, you don't see maybe very clearly, but here, A. Okay. Okay. There are different peaks depending on which part of the spectrum you are. You see, as you go towards the right, you're going towards the infrared. Okay. So you're going to lower frequencies, larger wavelengths, so makes sense. Ultraviolet it doesn't really have a peak, right? Maybe here, but you have here maybe the visible one, yeah, visible. And then here you have the infrared peak. All right. Are there any questions about the spectra of emission, absorption, emission lines? Okay. So then the question is, how does this all relate to temperature? Well, first of all, temperature is a measure of the average kinetic energy of particles. So there is already a relationship, because when particles move faster, that means they have a higher temperature. And if we're talking about energy, we are also talking about these transition levels and the energy, because the energy is related to the frequency, which is also related to the wavelength. So if you have an object that is incandescent, or if you have, for example, an object radiating energy, you should be able to use the Planck curve to model this object radiating energy. And you should be able to find a relationship between the temperature and the frequency and wavelength. So every object that we see, guys, even yourselves, you are emitting some sort of thermal radiation. This depends on the temperature. Now, please, temperature is not thermal radiation. Temperature is not heat. Heat is transfer of energy. Heat goes from warm objects to cold objects. And is measured in joules, but it's also measured in calories. A good example will be doing exercise. You are sweating, you are burning calories. Okay? Now, it's true that thermal radiation and heat depend on temperature. In the case of heat, there is also a factor called specific heat capacity, which we're not going to discuss because that's more Earth kind of local. In the case of the universe and astronomy, we talk about thermal radiation and temperature. And as you saw here in this equation, temperature is very important, right? So let's take a look. When we use the Planck radiation and we plot intensity versus wavelength, as you see there, we can see 3 different Planck curves for 3 different types of stars. For a red star, 3000 kelvins. For a star like the sun, 5800, 6000 kelvins. And for a bluish star, 15,000 kelvins and above. Now, what are those temperatures? Those are the surface temperatures. But as you can see, the peak for the 15,000 Kelvin star is in a different position than the other peaks. So hotter objects emit more light at all frequencies, and they emit a higher average energy. Well, I mean, it makes sense based on the equation I showed you on the board, right? But how can we relate frequency to wavelength? I mean, frequency to color or wavelength to color. The more blue an object is, the more frequency and the more temperature it has. Let's think in terms of the candle. What is the hottest part of the candle? Again,
This part would be like either the flame itself or somewhere like lower down.
so maybe if I show you a picture, we can actually visualize that.
Oh yeah, down at the bottom, yeah.
The blue part, right? The blue part is the hottest part of the candle. The same happens with stars. The bluish star, the hottest it is in terms of its surface temperature. Normally they range between 15, 20,000 to 30,000, 40,000 kelvins. Just for reference, the temperature of the sun, the surface of the temperature of the sun is 6,000 kelvins. And for reference, Proxima Centauri. What is Proxima Centauri, by the way? I said that on the first day of class. What is Proxima Centauri? Okay, Proxima Centauri, guys, is the closest star to our solar system. We don't really say a star because it's a red dwarf, but it's still a type of star, though. And it's a reddish star with an average temperature of 3,000 kelvins approximately. Okay. So there it is. So the lower the temperature, the higher the wavelength. All right, let me give you the last equation that you're gonna need for this chapter, which is Vion's law. Let me just see if I find you guys a picture here for later. Okay. Where is my pen now? Vion's law is how we relate temperature with wavelengths. the way you write it is normally wins like that. And is used in black body radiation, where lambda times temperature of the peak is equal to approximately 0.0029 Kelvin meter. Okay. So if you know the wavelengths, you can find the temperature. If I do that exercise with the sun we know is around 5,800 kelvins. I get 500 nanometers. So the wavelength of the peak of the sun is approximately 500 nanometers. So then we can look at the scale of visible light. And let me show you this. Can somebody tell me, looking at this, the wavelength of the sun, at which color is the peak? 500 nanometers, so where is it?
Blue?
Sort of like in here, right between blue, greenish here. Interesting, right?
Mm-hmm.
Expecting yellow. Well, I say it's not yellow, right?
Yeah.
Yeah, but that's just the peak. Remember that the sun is a combination of colors. So the peak wavelength of the sun is actually in the greenish part of the spectrum. That's a very interesting fact, but it is, right? So we are going to be using this on the lab. I want you guys to review this before Monday, because actually maybe, here, remember, the hottest will be a blue star, okay? If you guys go and take a look at the lab that we're going to do on Monday, here, we are going to be using everything that we discussed right now. We're going to be investigating or studying the spectra of different stars, and we're going to find their temperature. All right. It's a very nice lab. You can probably finish it in one day. We'll see. But also, I will give you also an idea of the classification of stars. So we can actually talk about that a little bit. Because depending on the color, we classify stars as well. Why don't we glow in the dark? Don't tell me we don't emit any kind of light, because if that was the case, they wouldn't be able to take your temperature. So it's not A. So why don't we glow in the dark?
B?
Yeah, you only emit basically infrared radiation, right?
Yeah.
That's how infrared. Now, based on what we have been studying, are infrared thermometers accurate? Are they reliable?
I think to a specific extent, right? Like they're not 100%.
No, they are not, right? So using them for the COVID is probably not the best way. They do give you an indication, but unless you have a very high fever, it won't really tell, right? The other factor is that, let's suppose it's a very cold day, like 20s, and you go to college, and most likely you're gonna find a machine where they take your temperature. is the machine gonna give you a lower value than you expect or a higher value than you expect?
Lower.
Lower, right? Because why? Your body is releasing heat
Very cold. Yes.
because it's, yeah, you're cold. So I mean, by the way, it happened. I've seen that in the one that we have here in the college. So they are not very reliable though. Okay, so the peak is very important, but we also want to understand the features that we see when we look at the actual spectrum of objects. All right. So when we study this, we can learn a lot about the object itself, not just the temperature, but the elements that are being produced by the object. For example, let me ask you a question, guys. What elements would you expect to be more abundant when you look at the spectrum of the sun?
Helium or hydrogen?
No, well, maybe a little bit, but the most abundant.
Hydrogen?
Hydrogen. The sun is still burning hydrogen to helium for 5 billion years more. So we still have more abundance of hydrogen. In 4.8 billion years, we'll probably have more helium, yes.
Mhm.
And also other elements that are in the upper, in the corona of the sun, mostly. But still, all right? We can tell that by analyzing the spectrum of the sun. The same we can do with other stars. Now, we can also do that with planets. Look at this. Carbon dioxide. Where would you expect to find carbon dioxide, guys? When you're looking at what? We're looking at planets. If we, for example, carbon dioxide is important or not for the planet? It's important because it's a greenhouse gas. That's how we get radiation. That's how we trap radiation. That's how we have temperatures that are not, that don't have large fluctuations like in the moon, right? The moon doesn't have an atmosphere and the temperatures are crazy. Or even Mars. If you just go to Mars, which is also in the habitable zone, right? Without an atmosphere, it's hell. And also really like cold. It can be very cold, very hot. It can be extremely cold, sorry. Not hell, like very, very bad. Ultraviolet emission indicates a hot upper atmosphere. We will see that a lot from Venus, for example. Well, we can also see that from Mars. Ultraviolet, but mostly the carbon dioxide. Okay. This is important. Okay. Guys, we're gonna, with this we finish. Actually, did we finish the chapter? Yeah, wow. Okay, so we're gonna be doing a review of this, don't worry, because we have to before that lab. Where's my pen? Okay. Let's suppose where you are, let's use sound first. Sound is also characterized with a wave sounds. The difference is that wave sounds need this, air. Light doesn't need a medium to be transferred, to move. Nobody can hear you scream in space, right? That's why. So if you are here and there is an ambulance or a police truck or a fire truck here, and it's sounding the alarm, you can hear it, right? Because there are waves coming to you. I want you to tell me what happens with the frequency at what you are hearing this if the ambulance moves away.
The lower frequency?
Lower, good. What will happen if the ambulance moves towards you?
It increases.
Good. That is called the Doppler effect or the Doppler shift. The Doppler shift for sound is the fact that sound waves, their frequency increases as the source is moving towards the person listening, or if the person is moving towards the source.
So it's specific to sound.
No, it also happens with light.
Okay.
When a light object, for example, a galaxy, is moving away or towards an object, the frequency changes. That's called a Doppler effect for light. That's called something that you probably have heard. The red shift. How many of you have heard of this? How many of you have heard of this red shift?
I haven't.
I have, yes.
Red shift is what we use in astrophysics to measure the speed of galaxies and stars moving away from us. Remember, Einstein theoretically discovered that the universe was expanding, but it was Edwin Hubble in the 1920s, by analyzing the spectra of stars, that the spectra was always moving towards the red. So if I show you the spectra of stars, let's use this. If I show you the spectra of stars, yes, what he found is that the line of emission, instead of being here, was actually here. There was a shift. That means that the wavelength was increasing. Let me ask you something. When the electromagnetic wave is moving away from you, what happens with the wave? It compresses or it stretches?
Stretches.
So then the wavelength has to increase and the frequency decreases.
Mhm.
That is the idea of the Doppler effect. I gave you the example with sound because it's something that you can relate in daily life. And we also have a Doppler effect for light. It's governed by the speed of sound. The Doppler effect for light is governed by the speed of light. There is an equation, but we're not going to do it. Okay, I mean, we could do it, but the demonstration requires special relativity because you require time dilation. The idea that time changes depending on the observer. Time is relative. For example, if you're moving at the speed of light, will you measure the same time as I am measuring? Yes or no?
Yeah.
No.
No?
The twin paradox. You can read about that, right? If one twin leaves at the speed of light to Alpha Centauri and comes back, he will be 8 years older. You will be 50 years older. That's because of relativity. When you go at the speed of light, time dilates. Okay, that was something that Einstein discovered, and it's been proven. How do you think we build atomic clocks? We build them according to that dilation that we know is happening. So that's interesting, right? Okay, so this slide actually summarizes this. They use blue and red to show you the blue shift as well. The shift is if the object is coming towards you. So in this slide, there is red shift for this guy, blue shift for it. And look at the wavefronts. The wavefronts come closer and closer as the object moves respect to this person. Everything is relative in the universe. That was, I think, in my opinion, and not just mine, one of the reasons why we think that Einstein was the greatest scientist of all time was because he actually introduced a crucial principle of the universe. Everything is relative. Time, energy, position, depending on who is measuring it. That's something that Galileo sort of had an idea, Newton as well, but Einstein was the one who did the breakthrough on this. Okay. So everything is relative, right? So you have two people in there. A good example is, let's suppose you are in the train. Will you measure Doppler effect? Yes or no? You have an observer outside, but then, okay, let's use mechanics. You have a ball and you are inside the train. And you throw the ball. What's the motion it has? If you are riding on a train and you throw a ball towards the air, it will land on your hand. Yes or no? Yes, it just goes up and down.
Yeah.
For a person outside, how does it look? It looks like a parabola, right? That is perception. That is relativity, right? So for the person outside, it looks like a motion in two directions because the ball is also moving at the speed of the train. So that is the concept of relativity. Anyway, so I want to finish with this today, guys. I gave you a lot of information, and I think what I'm going to do next class is I want to do more of the math, and I want to go over especially black body spectrum, and then we can do the lab. Okay, I strongly suggest you to start looking at this lab. All right, and then I will go over it, and then the aim is to finish it on Monday, because it's what? On Wednesday, I want to start with telescopes. Since telescopes do what? They use light. So we have to do that, right? And that will be the last chapter of the first 6 that we're gonna do. Then you guys go on a spring break, I know, but I will give you a few things to do. So that means when you guys come back, we're gonna start talking about the sun, stars, and a whole bunch of interesting objects. All right, guys. Are there any questions? Okay, before you go, the escape velocity doesn't depend on the mass. The escape velocity of any rocket, any satellite, any person that is trying to escape the planet is always 11 kilometers per second. If you remember, the equation canceled the mass. Remember, GMM divided by R equals to 100 mv squared. The mass cancels. You only depend on the mass of the planet, the gravitational constant, and the radius of the planet. Okay. All right. That was the only question I think I saw. I saw an error. Everything else was fine. Yeah, and then you guys can see your grades already. So that's it, guys. I'm going to stop the recording, and I'll see you guys on Monday.
See you, Professor.
See you guys.
Have a good rest.